Hello everyone. In this lecture, we'll talk about how to make signal generator circuits using op-amp. So earlier we've seen the application of operational amplifiers as mathematical operators, right? So we saw how to use an op-amp to make circuits that perform various mathematical operations like addition, integration, exponentiation. Today we talk about how to use op-amps to generate sinusoidal signals or square wave signals, triangular waves or pulse waveforms. This is another very important application of op-amps. So typically there are two approaches to make signal generators using op-amps. One is to use positive feedback along with a frequency selective network. Although the mechanism is largely nonlinear, in order to differentiate this from the other approach, these type of oscillators are called linear oscillators. The second approach is by using circuits called multi-vibrators, which are also constructed using op-amps, and these are called function generators or non-linear oscillators. In today's lecture, we'll look at this approach of making a sinusoidal linear oscillator. If the nature of oscillation is sinusoidal, it will be called a sinusoidal oscillator. If the oscillation is such that the signal remains at a certain amplitude for some time, then shifts to another level and then stays at that level for a certain time, then that would become a square wave or a pulse wave, depending on the shape of the signal which is being generated. Now, the keywords here are positive feedback and frequency selective network. We've talked about frequency selective networks before. Let us see what is the meaning of positive feedback. Now, before we talk about positive feedback, let us quickly revise how a negative feedback circuit used to look like. So, in negative feedback, which we would use to make an amplifier, we would have an op-amp circuit, a block A denoting the op-amp having a gain A. We would have an input and an output, say V0. A part of the output would be fed back to another network, the feedback network B. The output of the feedback network would combine with the input so as to oppose its polarity. That means if I was to write signs here, I would say this is plus and this is minus. I have a summer or an adder where the output of the feedback is subtracted from the input, and this is the result. Another convention that we are following is that if we have a block having gain say x, then given an input v, the output is v times x. Okay, that is a convention we are following. So if the input to the feedback circuit is v naught, the output is v naught times b. So we can say that v out is a times this signal, and this signal is v in minus b times v naught. That means a times v in minus ab v naught. We take this term to the other side, we get v naught 1 plus ab is equal to a v in, and we could write that the closed loop gain v out upon v in is a upon 1 plus ab. Right? This is the case of negative feedback because the part of the output was fed back but out of phase. So it was 180 degrees out of phase, hence this minus sign. If this was not negative feedback, if this was positive feedback, that means if this was positive feedback, this sign would be plus. That means a part of the output is being fed back in phase with the input. In phase means to reinforce the input, to regenerate the input. Okay, so it's called a regenerative feedback. The negative feedback is often called degenerative feedback because it's out of phase. It has an effect of opposing the effect of input. Positive feedback, however, means that the part of the output is being fed back in phase with the input. if that is the case, we have this would become plus v naught. We will have this term as plus, this term would become minus, and this is what you would get. A upon 1 minus AB, if this was a case of positive feedback. Now, another important thing to note is that when we were talking about amplifiers or mathematical operators and we looked at standard configuration, this network B used to be a purely resistive circuit. So we looked at a case where B was something like this. It was a purely resistive circuit. However, if the feedback circuit is a frequency dependent circuit or a frequency selective circuit, that means instead of the feedback being a completely resistive network, if it was made up of reactive elements along with the resistor, then this feedback circuit or this gain B, right now we consider B to be a constant because in an earlier case of negative feedback, we found that B was, when we had this kind of a circuit, we found that B, that is the gain of this feedback circuit, if this is the input to the circuit and this is the output, we found that gain B was simply R1 upon R1 plus RF. Right? This being V naught being the input, VF being the output of the feedback circuit. This is what we found the feedback gain to be. A scalar, because resistors do not offer any phase change. If this feedback circuit is no longer resistive but made up of reactive elements, this kind of a network, then the gain, that means say this is the input to this network and this side, because this is feedback, right? So this side is the input, this side is the output. Then the ratio of output upon input or the gain of this circuit will no longer be a scalar. That means it will no longer be independent of frequency. Why? Because the moment you have reactive elements, their reactances are dependent on frequency. So reactance of capacitor is 1 upon j omega c, where omega is the frequency of the signal, right? Frequency of V in. The moment reactive elements come into picture, the gain of the feedback circuit is no longer a scalar. It becomes a function of j omega. We already know that the open loop gain A is also not constant for all frequencies. So A is also in a way dependent on frequency. So A is also a function of omega. So this product AB, which is called loop gain, just this product AB, for a circuit which has a reactive feedback circuit or a frequency selective feedback circuit, the loop gain is also frequency dependent. Right? This is the role of frequency selective networks. Now, knowing that the loop gain is now frequency dependent at a specific frequency omega naught, if the loop gain becomes equal to 1, that means if at some frequency omega naught means 2 pi f naught, if at some frequency omega naught the product of A and B, if this becomes equal to 1, then what would happen? The denominator in this term will become 0. As a result, the closed loop gain would become infinity. What would that mean? It would mean that at this frequency omega naught, the circuit will have a finite output even for a 0 input, because the gain is infinity. An infinitesimally small input would still result in a finite output. Right? That means without an input, there would still be an output. This is what would happen if AB equals to 1. Another way of looking at it is, say we have a feedback network like this and have a switch block representing the op-amp. This is fed to a feedback network. To differentiate between those purely resistive feedback networks and reactive networks for this particular case, instead of B, we will use the term beta, just to differentiate. So if this is the scenario, and now feedback is given such that before the switch was closed, there is some input Vi. The output of this op-amp would therefore be A times Vi. That is what is fed into this feedback network. The output of the feedback network would then be beta times AVI. This, in this polarity, is fed back to the input, right, as positive feedback. Let me call this as Vf. Vf is nothing but beta AVI. Beta is the gain of the feedback network. If the values of A and beta are such that the product A beta results in this Vf being nearly same as this Vi, the input voltage, then when the switch is closed and this fictitious voltage that we applied in the beginning, even if we remove this Vi, the circuit would continue to operate since the feedback voltage is sufficient to drive this op-amp. If the value of A times beta was such that this feedback voltage becomes almost same as this input, this fictitious input voltage that we had chosen in the beginning, if that was the case, then even if you remove this input, it would be sufficient to sustain this loop operation. Now, to make Vf equal to Vi, we know that Vf is beta A Vi. For this relationship to be true, we can see that A times beta should be equal to 1. This is the same thing that we had arrived at from the previous case, and this condition, the loop gain being equal to 1, that is sufficient to sustain this loop operation, that even when there is no input, you would continue to get output. This condition is called Barkhausen criteria. It's named after the German physicist Heinrich Barkhausen. If this criteria is met, that means at that particular frequency. Now we know that A and B both are frequency dependent, right? So essentially we are saying that the condition where the product of A and beta for this particular frequency, when that product is equal to 1, if this criteria is met, then this circuit would generate a frequency of omega naught. In reality, no input is actually needed to get this operation going. Only this condition of Barkhausen criteria, only this condition is necessary, and it would ensure self-sustained oscillations, right? Practically what would be done, we'll have a setting. The circuit would be such that to start with, this product of AB would be greater than 1. No actual input is required to be given. Very small voltage like the noise, which is there everywhere, that noise voltage can serve as an initial voltage, and noise would be taken as the input, right? So some small fluctuations are there. Those fluctuations start getting amplified because we'll keep AB greater than 1. What will happen is after a while, op-amp circuit would reach saturation, and we would have non-sinusoidal output in certain part because A times beta is not exactly 1. After a while, there will be saturation in the op-amp. You'd still not get an accurately sinusoidal output, so this would be distorted, so it will be non-sinusoidal, which looks like sinusoid. But if we try to bring AB as close as possible to 1, then the signal will tend more and more toward a sinusoidal oscillator, because we know that it will be one particular value of omega naught at which this condition will become true. In other words, an infinitesimally small voltage can provide a measurable voltage. You don't really need to give an input voltage to start an oscillator, right? How does that become possible? Because when this Barkhausen criteria is met, at that point the closed loop gain of this circuit, of this positive feedback circuit, becomes infinite. That means even if you give a negligible input, it will be multiplied with a very, very large number, and it would result in a finite output. That is how the circuit can act as an oscillator even without any input being present. This was possible because in the denominator we had the term 1 minus AB, right? And this 1 minus AB term could come because we used positive feedback. This is how collectively, using positive feedback and using a frequency selective network, helps us make an oscillator circuit. So understand that A and B are frequency responses now. How we have studied in an earlier network where we used to have an input and an output, and we would say the frequency response is h of omega, right? Output upon input. So it's just another way of saying that the gain of such a system is h of omega. So instead of h, we now have a omega or beta omega. So this A and B are now frequency responses of the individual terms. A being the open loop gain, beta being the gain of the frequency selective feedback network. So it's interesting to note that the frequency of oscillation, it is determined solely by the phase characteristics of the feedback loop. Remember when we talked about frequency response, we would have a magnitude spectrum and a phase spectrum, the variation of angle with respect to frequency. This is what is meant by phase characteristics. So, what the statement says is that the frequency of oscillation, we of course wrote it in terms of A omega naught times beta omega naught, but the actual frequency of oscillation is determined solely by the phase characteristics or the phase spectrum of the feedback circuit. What does this mean? It means that the loop oscillates at the frequency for which the phase is zero. Remember, we said positive feedback means the part of the output is being fed back in phase with the input. That means the net phase difference between the part being fed back and the input, the net phase difference should be zero. As opposed to negative feedback, where output was fed 180 degrees out of phase with respect to the input. Here it should be fed in phase. That means the phase difference should be zero, right? So the loop oscillates at the frequency for which the phase is zero. Now, another thing is that the stability of oscillations. That means if I wanted to generate a signal of frequency omega naught, does it continue to generate the frequency of omega naught, or does omega naught keep changing? Does the frequency keep changing? The more stable the frequency is, the better is the performance of the oscillator. Otherwise, it serves no purpose, right? If the frequency keeps on changing. The stability of oscillation is determined by how the phase spectrum or the phase response of this feedback circuit changes with respect to omega. It is said that if the phase spectrum is steep, that means the regions of beta omega where the phase spectrum is steep results in more stable frequency. What does this mean? Say if I sketch angle beta omega with respect to omega, and if it is something like this, okay, there's some portion that we are referring to for a particular frequency omega naught, a certain portion we are referring to, and this is how the phase spectrum looks like. Now, due to any change in the circuit parameter, say the temperature changes, and as a result, overall value of RC changes. That's why the phase angle changes. Say if the phase changes by an amount delta, so this is the change in phase, the corresponding change in frequency would be much less if the slope is steep. If due to any changes in the circuit, say change in temperature, if the angle changes, if the phase difference changes, if the phase response is steep, then that change in angle will not affect the frequency significantly. The steeper the value, even less would be the corresponding change in the frequency. If the derivative of this phase response is large, the resulting change in the oscillation frequency is small. That means it is more stable. Okay, so let us take an example of an oscillator, also called an RC phase shift oscillator. From the name, it suggests that the feedback circuit, the frequency selective circuit of this oscillator, will comprise of R and C. So this is how the circuit looks like. In the feedback network, we have an array of 3 RC networks. Now you must be wondering if this was supposed to have positive feedback, right? So how are we going to obtain it? By connecting it to the inverting terminal of this op-amp. Now positive feedback means the overall phase difference should be 0. That means it is crucial for this frequency selective network to produce a cumulative phase change of 180 degrees. And then when you connect it to the inverting terminal, it's going to give it another 180 degrees in phase shift. As a result, the total phase shift would be 0 degrees. And that is how this would give a positive feedback, a net phase difference of 0 degrees. The feedback network, the frequency selective feedback network, should produce a total phase shift of 180 degrees, and connecting it to the inverting terminal would give another 180 degrees, producing a perfect positive feedback. We've already discussed the behavior of such a network, giving an input across this pair of terminals with respect to ground and measuring output here. This is what we're trying to do. That is what is going to be fed back. If we use typical network analysis, we can find that the frequency of such a phase shift oscillator having 3 equal capacitors of value C and 3 equal resistors of value R, the frequency of oscillation comes out to be 1 upon 2 pi root 6 times RC. More generally, this would be 1 upon 2 pi root 2n times RC, where n is the number of cascade stages. So here we have 3 stages of RC, so n equal to 3. Now we've already discussed this kind of a network before. If you recall the frequency response of a high pass filter, where this is where you would give the input and you would measure output and you would look at the frequency response or the gain of this circuit, right? This is exactly the same thing. So if you flip it and draw, this is exactly what you would get. Now remember that we said that this kind of an RC circuit, one such stage of an RC circuit, could help us achieve a maximum phase shift of 90 degrees. We just want that the feedback circuit should give us a total phase shift of 180 degrees, right? So theoretically speaking, why didn't we use just two stages of such an RC circuit? But if you remember the phase spectrum of such an RC circuit, it looks something like this. This is how the phase spectrum looks like. Now you notice that for the range of values where phase is approximately 90 degrees, the phase response is very flat. Therefore, even if we use just two stages and get an effective phase shift of 180 degrees, because the phase spectrum is flat around this area, we would not get very stable oscillation. That means the frequency will not be stable. That is what we just discussed just a little while ago. That how having a steep phase response would result in more stable frequency, right? Because the change in phase will not affect the frequency of oscillation much. So this is why it's not feasible to use just two stages of RC and solve this, which is why we use three stages. The idea is that, again, theoretically, you would think that each of these three stages produce a phase shift of 60 degrees each, and as a result, because they're identical, the net phase difference would be 180 degrees. Again, practically speaking, because they are cascaded, that means they are connected in series, like another stage is connected at the output of one stage. The stage which is connected next produces a loading effect. That means the next stage acts as a load. Means, say we have first stage having value C1 and R1, right? This is connected to another stage. So this is connected to another stage. So this is C2, R2. So the output impedance of this stage, the first stage, is changed because of the second stage because they are connected in parallel, right? So the changing of this output impedance of the filter in this way, each of the succeeding stage is going to create a loading effect. The change in output impedance of the filter in this way causes the frequency at which they are meant to produce the required phase shift to change. That means it's going to end up changing the oscillating frequency if you have more and more such stages. So more the number of such stages, more is the loading effect. Okay, so we just saw that two is not sufficient and four or more would make it a little more complex. That's why this three stage is a popular choice. Four stage circuits are also used, which each have a 45-degree phase shift, but three is one of the most popular choices. This is an example of an RC phase shift oscillator that employs positive feedback and an array of cascaded RC stages. The role of the feedback circuit is that collectively the total phase shift that it should give should be 180 degrees, and connecting it to the inverting terminal would produce another 180 degrees, effectively resulting in positive feedback. The particular condition when the Barkhausen criteria is satisfied results in this frequency. This is an example of a linear oscillator which is constructed using an op-amp in positive feedback and a frequency selective network. The other approach of making function generators using multivibrators that we'll discuss in the next lecture.